Welcome back to Lesson 4 of the e-learning course 0, Basics of Finance. In session 4.3, we will study how to use the NPV-IRR rule to make investment decisions. The learning goal of session 4.3 is to illustrate how to make investment decisions by applying the NPV-IRR rule properly. In this context, we will touch upon different problems that can occur in practice when using these rules. Sometimes you have to make a choice today that will have an impact on future opportunities. When this is the case, choosing between competing investment projects is trickier. There are at least 4 important problems to be aware of. The first problem is the investment timing problem, meaning should you invest now or wait and think about it again next year. The second problem is about the choice between long and short-lived equipment. In this context, the company has to decide to save money today by installing cheaper machinery that will not last as long, or buy equipment that's more durable but also more expensive. The third problem is the replacement problem, when it's about the decision when to replace existing machinery. The final problem is about the cost of excess capacity and asks the question, what is the cost of using equipment that is temporarily not needed? We will look in detail at each of these problems on the next few slides. It might be tempting to think that a project with a positive NPV is best undertaken now. It might be the case that the same project is even more valuable in the future. If we assume cash flow streams are certain, the optimal timing is pretty straightforward, as you will see in a second. For that purpose, let us assume that the net present value of the harvest of timber at different future dates is as follows. By assuming a discount rate of 10% and discounting the net future value back to the present, we find the year that maximizes the net present value of the investment today. In this example, the year of harvest is supposed to be in year 4. The next problem we have a closer look at is related to the choice between long and short-lived equipment. Suppose a firm has to make a decision which machine to buy. The choice is between 2 machines that have identical capacity and do exactly the same job. Machine A costs $15,000, has operating costs of $5,000 and a running time of 3 years. Machine B has initial costs of only $10,000, slightly higher operating costs of $6,000 and a running time of 2 years. Computing the present value of these costs for each machine using a discount rate of 6% implies that the present value of machine A corresponds to $28,370, while the NPV of machine B is $21,000. However, to make an investment decision, we have to determine the annual costs of buying and operating each machine over its lifetime. For that purpose, we compute the so-called equivalent annual costs. This is done by finding the 3-year annuity with the same present value as the lifetime cost of each machine. The annuity payment is computed as the present value of the annuity divided by the 3-year annuity factor. Doing this computation for machine A yields an annual annuity payment of $10,610 and an annual annuity payment for machine B of $11,450. Comparing the equivalent annual costs implies that machine A is a better choice since these costs are lower. The next problem deals with the question when to replace an old machine. Suppose you're operating an elderly machine that is expected to produce a net cash inflow of $4,000 in this year as well as next year. Assume that after 2 years, the machine won't run anymore. The old machine can be replaced today with a new machine that costs $15,000 but is more efficient than the old one and will provide a cash inflow of $8,000 a year for 3 years. The question you've been asked is, should you replace your equipment now or wait a year? In order to answer this question, we use again the concept of equivalent annual costs. In the table, you see an overview of the cash flow streams and the NPV of these cash flows at the 6% discount rate, as well as the equivalent annual cash flows. Since the cash inflows of the old machine exceeds the annual cash flow of the new machine, it makes no sense to replace the old machine with a new one today. Even if you consider a salvage value of, say, $8,000 in this year and $7,000 next year. If you wait a year, your opportunity costs are today's salvage value plus a year's return on that money, which corresponds to $8,480. The loss is then $1,480, which is the difference between opportunity cost of $8,480 and next year's salvage value of $7,000. Even when considering the higher salvage value, you shouldn't replace the machine. Another problem to discuss is related to the costs of excess capacity. Suppose we have a new investment project that requires heavy use of an existing information system. However, the effect of adopting the project requires the purchase of a new, more capable system forward from year 4 to year 3. Moreover, assume that the new system has a life of 5 years, and at a discount rate of 6%, the present value of the cost of buying and operating the system is $500,000. If we undertake the project, additional costs of $118,700 occur in year 4. When we apply the 6% discount rate and discount these additional costs to the present, we obtain a present value of $94,000, which has to be charged against the new project in order to decide whether it should be realized or not. After having carefully studied session 4.3, please start with the review questions.